All right. It says figure 17 shows the derivative f prime of x on the interval from 0 to 1.2. Locate the points of inflection of f of x and the points where the local minimum and maximum occur. Determine the intervals on which f of x has the following properties. Okay, so let's make a sketch. So we got 0.17, 0.4, 0.64, 1, and 1.2. And then our graph is going to go through at 0, and it's going to cross at 0.4. Looks like it has a max at about 0.17. Looks like we have a min at about 0.64, and then another max. Okay. So something like this. Okay, that's our graph. And the first thing they ask is locate the points of inflection of f of x and the points where the local maximum and minimum occur. Determine the intervals on which f of x has the following properties. Okay, so what we're looking at is f prime of x. So what I would do is I would draw a number line. I would actually draw two number lines. And I would be wanting to look at f prime of x and also f double prime of x. And actually I'm going to do a little bit of room so I can think about what I know. All right, now remember, let's do what I think is kind of easy first, which is just I'm looking at the first derivative. So I'm going to talk about where the function is increasing and decreasing based on looking at the first derivative. So if you look at the first derivative, and you want to talk about the original function, you're concerned where the first derivative is equal to 0 or is undefined. But in this case, it's just equal to 0. It's all we have. So 0, 0.4, and 1 are all, they are all what we would call critical points. Okay. Now, we notice that then we want to know the sign, whether it's positive or negative. The derivative is positive or negative. Well, from negative infinity to 0, we are getting negative y values. Then between 0 and 0.4, you can see that you have positive y values. Between 0.4 and 1, you have negative y values. And then from 1 to infinity, you also have negative y values. Okay, so it seems that the original function, or we know that the original function f will be decreasing on the interval from like negative infinity to 0, and then it will be increasing from 0 to 0.4, and then it'll be decreasing for the rest of the time. And actually at the instant at 1, the original function is going to be flat. There's a flattening right there. That the reason that if for it to be a possible critical point, but not a max or min, you either have a vertical tangent there or you have a flattening there if it doesn't become a max or min. Does that make sense? So it must get real flat just at that moment. All right, so if it's decreasing and then increasing, we have a max. And then increasing and then decreasing, we have a min at the 0.4, and then we realize that this is just flat. If I then asked you to sketch the original function or something, you'd want to indicate that flatness. Oh, absolutely. As I drew it, I'm sorry. That's a min, and then increasing, decreasing, that's a max. Sorry, I have no idea. And then flat. Okay. All right, now let's look at the second derivative. All right, remember the first derivative, the behavior in terms of increasing, decreasing max mins of the first derivative is going to tell you the sign and also the critical points of the second derivative. I mean, they're not called critical points, they're possible points of inflection. So the possible points of inflection that we have for the original function will be at 0.17 and 0.64 and 1. Okay? So what we're going to do now to decide whether the second derivative is positive or negative is look at, since we have a graph of the first derivative, if the second derivative is positive, then the graph of the first derivative must be increasing there, right? And if the second derivative is negative, then the graph of the first derivative will be decreasing. Okay, so looking at the second derivative, looking at the derivative, we can determine that from negative infinity to 0.17, we get positive second derivative values. And then from 0.17 to 0.64, we are having negative second derivative values because our first derivative is decreasing, which means that our second derivative will be negative there, which means our original function is concave down there. Okay, now between 0.64 and 1, our first derivative is increasing, so that means you have positive second derivative values there, and it tells you that the function is, the original function is concave up there. And then notice our derivative is decreasing, so that's why we're going to have negative values for our second derivative. Okay, and so what does that tell you about f? It's concave up, concave down, concave up, and then concave down. So we have a point of inflection at 0.17, a point of inflection at 0.64, and a point of inflection at 1. So that flattening, when you have that flattening at 1 on the original function, say here at 1, it was decreasing, but it's concave up, and then it flattens, and then it's concave down. So that's kind of what the original, now it may not be crossing the x-axis there. It could be up, we don't know where it is, that figures, that shape's occurring, but that's what it means. Does that make sense, Jill? Okay, so did we answer the questions pretty much? Increasing, concave up, decreasing, concave down, local min and max, and points and place. So we did pretty much answered all of their questions on number 23. Before I